Hey there, science explorers! Welcome to an exciting journey where we unravel the mysteries of energy and its transformations. Today, we're diving into the fascinating world of thermodynamics. This branch of physics is all about understanding how energy moves and changes in different systems. Thermodynamics is the study of how energy transforms in physical systems. It's like the science of energy magic, showing us how energy can change forms and move around. It helps us understand why some processes happen spontaneously, like ice melting on a warm day, where the heat from the surroundings causes the ice to turn into water, while others need a little push, like baking a cake. Here we need to add heat to the ingredients to transform them into a delicious treat. Thermodynamics can be a bit tricky, but don't worry. We'll use simple language and everyday examples to make it crystal clear. We'll break down complex ideas into easy-to-understand concepts. We'll explore three key concepts: Gibbs, free energy, enthalpy, and entropy. These are the building blocks that help us understand energy changes. Together, they hold the secrets to understanding energy changes in the world around us. Imagine them as the keys to unlocking the mysteries of how energy works. So buckle up and get ready for an awesome journey into the fascinating realm of thermodynamics. We're about to embark on an adventure filled with discovery and fun. Before we dive into the specifics, remember that energy is the ability to do work. It's what makes things happen, from lifting weights to powering our homes. Work can be as simple as moving an object or as complex as driving a chemical reaction. It's all about making things move and change. And heat, a form of energy, always flows from hotter objects to colder ones. This is why your hands get warm when you hold a hot cup of cocoa. Now let's embark on our thermodynamic adventure. Get ready to explore, learn, and have fun as we uncover the wonders of energy and its transformations. First up is Gibbs free energy, named after the brilliant scientist Josiah Willard Gibbs, who made significant contributions to thermodynamics and physical chemistry. This powerful concept helps us predict if a process will occur spontaneously, meaning without any external help. In other words, it tells us if a reaction can happen on its own. Here's the deal. Gibbs free energy, symbolized by G, combines enthalpy, heat content, H, and entropy, disorder, S, in a neat equation, G equals sign HTS, where T is the temperature in Kelvin. This equation is a cornerstone in understanding chemical reactions. Don't let the equation scare you, we'll break it down. It's simpler than it looks once you get the hang of it. Think of it like this. Imagine you have a wallet with a certain amount of money, Gibbs free energy. This money represents the energy available to do work. You can spend it on things you need, enthalpy, which are essential and necessary for survival. Or things you enjoy, entropy, which add to the disorder but bring joy and satisfaction. The temperature acts like a multiplier, making entropy more important at higher temperatures. This means that at higher temperatures, the disorder or randomness, entropy, plays a bigger role. If a process has a negative Gibbs free energy, dg 0, it's spontaneous. This means the process can happen without any additional energy input. It's like having enough money in your wallet to buy that awesome toy you've been eyeing. You don't need to borrow or find extra money. But if dg is positive, the process won't happen on its own. It needs extra energy, like borrowing from your piggy bank. This means you need to add energy to make the process happen. Now let's focus on enthalpy, H. Enthalpy represents the total heat content of a system. It's like a measure of the system's internal energy plus the energy needed to make space for it under constant pressure. When a process occurs, the change in enthalpy, dH, tells us if heat is released or absorbed. Exothermic reactions release heat into the surroundings, dH0, like a bonfire warming you on a chilly night. Endothermic reactions, on the other hand, absorb heat, dH0, like baking a cake that takes in heat from the oven. Enthalpy is a crucial factor in many chemical reactions and industrial processes. For instance, knowing the enthalpy change helps engineers design efficient combustion engines and safe explosives. Understanding enthalpy is key to controlling and utilizing heat in various applications, from powering our homes to developing new technologies. Our final stop is entropy, S, a measure of disorder or randomness in a system. Entropy is a fundamental concept in thermodynamics and statistical mechanics. and it plays a crucial role in understanding how energy is distributed in physical systems. The more ways you can arrange things in a system while keeping its overall state the same, the higher its entropy. This means that systems with high entropy have a lot of possible configurations, making them more disordered. Think of your room. A clean room with everything in its place has low entropy. Everything is organized and there are fewer ways to rearrange the items without changing the overall appearance. But if you leave clothes on the floor and toys scattered around, entropy increases. The room becomes more disordered and there are many more ways to rearrange the items without significantly changing the overall messiness. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This means that natural processes tend to move towards a state of higher disorder or randomness. It's like the universe's way of saying things tend to get messier. Over time, systems naturally evolve towards higher entropy, leading to the spread of energy and matter. While this might sound chaotic, entropy is essential for life. It allows for the flow of energy and the occurrence of chemical reactions that sustain living organisms. It drives many natural processes, from the mixing of gases in the atmosphere to the transport of nutrients in our bodies. Without entropy, the dynamic and ever-changing nature of life would not be possible. Section 5. Melting ice. A refreshing example. Let's illustrate these concepts with a familiar example: melting ice. When ice melts, it absorbs heat from the surroundings, which is endothermic, meaning dH is greater than 0. The water molecules transition from a highly ordered crystalline structure, which has low entropy, to a more disordered liquid state, which has higher entropy. At temperatures above 0 degrees Celsius or 32 degrees Fahrenheit, the increase in entropy outweighs the positive enthalpy change, resulting in a negative Gibbs free energy, or dG, less than 0. This means melting ice is spontaneous above its melting point. Melting ice is a classic example of how enthalpy and entropy work together to determine the spontaneity of a process. Section 6. Burning wood energy release and transformation. Another illustrative example is burning wood. This process releases a significant amount of heat and light, making it exothermic with a negative enthalpy change. The complex molecules in wood break down into simpler molecules like carbon dioxide and water, which are more disordered, indicating higher entropy. The large negative enthalpy change, combined with the increase in entropy, results in a highly negative Gibbs free energy. This means burning wood is a highly spontaneous process, explaining why wildfires can spread so rapidly. Burning wood showcases how enthalpy and entropy drive combustion reactions, releasing energy and increasing disorder. Section 7. Rusting iron, a slow but steady change. Rusting iron is a slower process but equally intriguing from a thermodynamic perspective. When iron rusts, it reacts with oxygen in the air to form iron oxide, releasing a small amount of heat, making it exothermic with a negative enthalpy change. The rust has a more disordered structure than the original iron, indicating higher entropy. While the enthalpy change is negative, it's relatively small compared to the entropy increase, especially over long periods. This leads to a negative Gibbs free energy, indicating that rusting is spontaneous, albeit slow. Rusting iron highlights how even seemingly insignificant enthalpy changes can lead to spontaneous processes due to the entropy factor, especially over time. Section 8. Photosynthesis, nature's energy conversion. Photosynthesis, the process by which plants convert sunlight into chemical energy, provides an interesting contrast. In this case, plants use sunlight to convert carbon dioxide and water into glucose, or sugar, and oxygen. This process requires energy input, making it endothermic with a positive enthalpy change, and results in a more ordered structure, indicating lower entropy as complex sugar molecules are formed. The positive enthalpy change and decrease in entropy lead to a positive Gibbs free energy. This means photosynthesis is not spontaneous and requires a continuous input of energy from sunlight to drive the reaction. Photosynthesis demonstrates that even non-spontaneous processes can occur with external energy input, highlighting the importance of energy flow in biological systems. Section 9. Conclusion. The interplay of energy, heat, and disorder. In conclusion, understanding Gibbs' free energy, enthalpy, and entropy is crucial for comprehending the world around us. Gibbs' free energy acts as a master predictor, telling us if a process will occur spontaneously based on the balance between enthalpy, or heat content, and entropy, or disorder. Melting ice, burning wood, rusting iron, and even photosynthesis showcase the interplay of these concepts in everyday phenomena. By grasping these fundamental principles, we gain a deeper appreciation for the driving forces behind chemical reactions, biological processes, and the natural world as a whole. So keep exploring the fascinating realm of thermodynamics, and remember, there's always more to learn.